Welcome everybody. We are Mariona Gibert, Arturo Guerra, and me, Ferran Batllori, and today we're going to solve exercise 7.1. Here you can find the statement of the problem. If you haven't read it yet, you can pause the video here. Otherwise, we're going to start solving it. Here we can see the formulas and concepts that we are going to use during the resolution of this problem. These are the Faraday's law, the magnetic flux, and the magnetic field of a solenoid. But first, we're going to stop in the Faraday's law. Faraday's law tells us that a varying magnetic field induces an electromotive force in a loop equal to the derivative of the magnetic flux through the loop. Here we can see the formula. The minus sign is a consequence of Lenz's law, which tells us that the electromotive force is contrary to the variation of flux. When we move a magnet through a wire, where there's a current flowing through it, a voltage is generated. This phenomenon is called electromagnetic induction. Here you can see this phenomena in the photo below. Now let's start with the resolution. Here the problem tells us the following. There is a long solenoid with a coil inside. The current in the solenoid produces a magnetic field, which affects the coil inside. Then the current in the solenoid is reduced to zero. As the Faraday's law states, the variation of the magnetic field induces an electromotive force. In this case, the reduction of the current will produce an electromotive force. Here we can find all the data necessary, and they are asking us about what's the electromotive force produced. Here we can see also a draw that shows us what's going on in this problem. Now let's start solving this exercise.
So we will start by computing the general formula of what we are asked to find. As you can see, the electromotive force is equal to the derivative of the magnetic flux divided by the derivative of time, which we can represent as the difference between the final and the initial situations of flux and time. Once we note down this formula, we evaluate the flux in these situations, knowing the magnetic field is equal to magnetic permeability times turns density times current, where turns density is equal to the number of turns per unit length. Once we have the magnetic field formula, we proceed to do the calculations. In the initial position, we have initial time equal to 0 and the initial flux equal to the integral of a surface, which is ds times b. We develop and end up having the expression you see. In the final position, time equals 25 times 10 to the minus 3 seconds. But the flux is 0 due to the change in current. The statement tells us, making the current at the end of the solenoid null. We then substitute values in the initial VMF equation and end up having it is equal to 75 millivolts.
To end up, let us propose a final question. What would happen if instead of giving a concrete time, the current was in function of t? According to Faraday's law, the magnetic field will induce an electromotive force. Again, the variation of the magnetic field will be produced by the variation of the current. In this case, as it is a solenoid, the magnetic field will be defined as mu times n times the current function. Consequently, and taking into account that the surface and the magnetic field are perpendicular, the magnetic flux will be defined as mu times n times p r squared times the current function. For instance, imagine that the statement defines the current function as minus 60t plus 3 halves. In concrete, this equation satisfies this condition of the exercise 7.1, in which the current is 1.5 amperes when the time is 0 and the current is 0 when the time is 25 milliseconds. Using the method of the previous slide and substituting all the information, we obtain that the electromotive force is 75 millivolts, which is the same result we obtained in the first method.